Okay, so this is our last topic for the course, and we'll be discussing about pumps. Pumps are fluid devices that converts the mechanical energy, often from an electric motor or internal combustion engine, into hydraulic energy possessed by the flowing fluid. And that hydraulic energy is in terms of position, pressure, and kinetic energies. Right here in the figure, we have here an example of a pump used for irrigation, and this pump is being driven by some external prime moving device. In this case, this is an internal combustion engine. So what I was saying is that the mechanical energy from this internal combustion engine, or from the shaft of this internal combustion engine, is being transformed into up to this point that's still a mechanical energy. For the pump, of course, there's going to be losses, but um, the final transformation is that from this mechanical energy, then it's being transformed into a hydraulic energy possessed by this flowing water. Okay, so um, that made it possible to to tap a water from a lower source or from a lower elevation and then discharge that into a higher elevation. Okay, so here's our pump, and this one is the suction side, and here's our discharge side. So the suction side is tapping from a lower source and then discharging it to some higher elevation, right? So just it's just simply because of this mechanical energy from this, of course, from this prime moving device, and then the mechanical energy that's rotating the impeller right here, and then transforming that, heating that fluid in the chamber, and somehow that increases the energy of the fluid, right? So that made it possible to lift the water from a lower elevation to higher elevation, or to transport the water from to some distances, and even to travel across some resistances. Okay, so actually there are many applications for pumps, and let's discuss some of the applications. So right here in our lecture handouts, it says that pumps are found in many applications, such as in buildings where they are used to elevate the water supply to higher level. So for example, we have a multi-level buildings. Then of course, if it's a building or it's a residential building, then there must be a water supply line. So how do we deliver the water from the from from a source, usually at the ground level source? So how do we deliver that into each floor level? So of course that would be possible if we use a pump, and of course sometimes there's gonna be a, let's say, a water tower, water supply tower. Then, but even even in that case, how do we lift the water from this level to that level? Then that's because of pumps. Okay, so another application is in automotive systems. We know that in automotive systems there are actually a lot of fluids. One example is the fuel supply systems. So how does a fuel travel from the fuel tank, for example, up to the up to this cylinder, right? Up to, I mean, up to being injected into the cylinder. Of course, there's gonna be some pumps right here, right? So I'm not using a proper notation. Let's just say there must be a pump, right? So here's our fuel tank, let's say, and how does the fuel travel, or is being transported from this fuel tank to the until it is being injected into this combustion chamber? Then of course there must be pumps. Okay, what else? In agricultural engineering, then pumps are found in process equipments, waste management systems, like for example the liquid waste slurries. Then if it's being transported or removed from a storage tanks, for example. So those are the applications. And also in irrigation and drainage engineering, aquaculture systems, and evaporative cooling pads, and even in fluid power systems in agricultural machineries. So actually, there's a lot of applications of this pump device. Okay, so now let's talk about some introduction. Okay, so fluids are moved through pipes or equipment or the ambient atmosphere by pumps. We can use actually pumps, fans, blowers, and compressors. Recall that we mentioned that in our previous topic that these are so pumps, fans, what else? Blowers and compressors. So these are fluid moving devices. And when we say fans, blowers, and compressors, they're usually for air or let's say vapor or gases. But for pumps, this is for liquids. Okay, so now let's talk about the types of pumps. By the way, before that, I just would like to show you this actual pump. So as I was saying, there must be an inlet or a suction side. So here it is. Here's the suction side. This is where the water enters into this chamber right here, and then it exits right there. Right. So if we try to open this, what we'll see is this one. So we have this impeller right here. So that's the that's the part where the water is being hit by this blades or these vanes, and that somehow adds energy into the flowing fluid, right? So here's the impeller. But this is just one type of pumps because there are many types of pumps and also different principles of operations. Alright, so now let's talk about this general classification of pumps. We have here in this figure a general classification of pumps based on this Hydraulic Institute, and this one is taken from this one of our reference material, Introduction to Hydraulics by Cruz et al. Right, so right here we have positive displacements, we have kinetics, and actually there's a lot more other subtypes right here. But for discussion purposes, then we'll just limit our discussion to this kinetic and positive displacements, and then just some few examples right here. Right, so let's write it here. Here's our pumps, and we said that generally there are two classifications. We have positive displacement, and we have kinetic pumps or dynamic pumps. Right, so from the word itself, actually, there's a difference in terms of how they add energy into the fluid. Because when you say dynamic pumps or kinetic pumps, then that means it adds energy by actually applying some force, and that force actually the intention is to increase the momentum or increase the speed of the fluid as it travels across that, or as it travels in that pump. Right, so for example, we have here this centrifugal pump. Right, so here's our centrifugal pump, and we know that there's an impeller. There's this device called impeller, or something like a blade. And the idea is that as the fluid enters right here, then as the fluid enters in this suction side, then it's being hit by this impellers right here. So in a way, there's going to be some transfer of forces, and the main idea is actually to increase the speed of the fluid, right? So in that way, of course, it's going to be related to the increasing the energy. Whereas when say positive displacement pumps, it's from the word here displacement, then it's more on or the intention is actually to displace some volume of fluids, and thereby somehow in that displacement of fluids, then there's going to be some increase in the energy. So a typical example is this piston pump. Right, so we have this inlet side and we have this suction side, and of course there's going to be valves right here, and there must be some pistons that's oscillating, or sorry, reciprocating, right? So there must be some piston, right? So this piston actually moves up and down, right? So when it moves, when the valve right here is open, let's say here's our inlet and here's our outlet. So when this inlet valve is open and this one is closed, then that means the water can enter right here, and of course it's gonna pull it. It will draw some fluid inside this chamber, and then in its forward stroke, then the valve right here will be closed, and then this one will be open. So the idea is that we have this batch of volume of fluid that's being trapped inside, and then it's trying to force this volume into this, or it's trying to displace this volume into this smaller space, right? So somehow that increases the energy of the fluid. Of course, whether we think about positive displacement or dynamic pumps, of course there are forces involved, but the intention is that when we say dynamic pumps, it's more on the the additional of energy to that moving fluid is actually through the heating action of this impellers. So somehow it's about increasing the speed or increasing the momentum of the moving fluid. Whereas for positive displacement pumps, it's more on the displacement. Although we are just talking about displacement, of course we know that there are forces involved as well. But the idea is that it adds energy by trying to displace this volume of fluid, or this trapped volume of fluid into this smaller space. So somehow that adds energy, right? So furthermore, this positive displacement pumps is further classified into reciprocating, and rotary. Right, so from the word itself, when I say reciprocating, then that means it's a linear motion. That's an example is this, a piston pump, but of course a reciprocating piston pump, because it's also possible to have there's also a rotary piston pumps. So this one rotary, that means that the motion of the pump, or the design of the pump, is in rotary motion, whereas this one is in reciprocating motion, right? So there's actually many types right here. Let's just write some few. So we have gear pumps, we also have vane pumps, and we also have piston pumps, right? And right here in dynamic pumps, there's also many types, but let's just limit our discussion to centrifugal pumps. Right, so here it is. Here's an example of the types of positive displacement pumps. You have this reciprocating pistons, and here's an example, or here's the illustration for gear pumps, and this one is illustration for centrifugal pumps. Now, just a couple of notes right here. In this piston or reciprocating piston type of pumps, actually this one is in rotating motion, except that the pistons actually right here, it's attached to this swash plate. So this plate actually moves up and down. It moves in these directions, something like this. So somehow the piston right here, the piston actually moves up and down, right? So still even though this one is rotating, this one is in linear motion or reciprocating motion. So it enters right here, but as this rotates, somehow because of the geometry or the design, then at some point, at some degrees or at some revolutions, then it will be transported or displaced into this exit side. Right, so that's it. And for these gear pumps, here it is. We have the suction side, and then it's being transported to the discharge side. Right, so it's a rotary motion. For dynamic pumps, centrifugal pumps, so water enters right here, and then it is being hit by this impeller and then discharged to this side. Right, so the characteristics of these positive displacement pumps is that usually it is characterized as having high pressure but low flow rate. Whereas for dynamic pumps, it's more on let's say more or high flow rate but low pressure. Of course, lower pressure as compared to this positive displacement pumps. So the applications are, because of these characteristics, then the application for this is usually for lower viscosities, like for example for waters, lower viscosities, fluids, of course liquids. Whereas for this one is used in hydraulic systems wherein the fluids or the liquids have higher viscosities, like for example oils and slurries, so higher viscosities. Right, so those are the characteristics of this two major classes of the pumps. Let's now move on to pump fundamentals. And by the way, these pump fundamentals or the equations that we'll encounter here is just for dynamic pumps and specifically the centrifugal pumps. Right, so water, the first equation that we'll discuss is this water horsepower. So just like our discussion with the fans and blowers, that we have this air horsepower, then for pumps, then of course there's going to be the hydraulic power or the energy added by the impeller to the water or the fluid as it moves through the pump, and that's what we call the horsepower, water horsepower. And the equation is, we have here WP for water power is equal to the flow rate Q times the weight density times the head or the pressure head or the pump head. Right, so water power, that's in watts or sometimes in HP. And for this volumetric flow rate, that's cubic meters per second or feet cube per second. And this one is the unit weight of the liquid. And if it's a water and in standard condition, then the SI units is simply 9.81 kilonewton per cubic meter. And for English units, we have the 62.4 pound force per cubic foot. Okay, so next one is, let's talk about the pump head or pump pressure. Right, so pump pressure, so just like our discussion with fans and blowers, we have the fan pressure where we apply the Bernoulli's equation. Now for pumps, we have here the total head of the pump, or the H sub T, or let's write capital HT, or the total pump head. That's just simply the comprises of the, I mean, in this pump jargon, they say this as a static head, just simply static head, and dynamic head. Right, so except that it's not exactly the same as the static head as what we mentioned in fans and blowers, because right here when you say static head, it consists of two head terms. So one is the pressure head and the other one is the elevation head. Right, so that's the total, actually that's what we call total static head. And for the dynamic head, and that's going to be that comprises for this velocity head plus the head losses. Right, so for example, here's our pump system. So we have this lower source, and here's our higher source, and here's our pump, then that means that this is going to be our suction side, and this will be our discharge side. Right, so let's say we'll not consider atmospheric pressure, but rather there's going to be some pressurized systems, pressurized conditions right here, and also a pressurized conditions right here. Right, so there's going to be P1 and P2. Right, so that means that for our pressure difference, there's going to be P sub 2 minus P sub 1, and divided by this unit weight of the liquid, and that's going to be our pressure head, right? So you recall in our Bernoulli's equation, we have, what's this? P1 by this unit weight plus V1 squared all over 2G plus Z sub 1, right? So plus the, of course, the head of the pump, let's just say, let's just write this. H pump is equal to P sub 2 divided by this unit weight plus V sub 2 squared all over 2G plus Z sub 1 plus head losses. Right, so recall that if here's our pump, then, and let's say here's our system, then of course there's going to be energy of the flowing water that's entering the system, and we have this energy exiting the system, and that energy is also for the flowing water. So we have your P sub 2 plus V2 squared all over 2G plus Z sub 1, and this one is all over 2G plus Z sub 1, this one is Z sub 2. Right, so the energy input for the pump, that's going to be our pump head, H pump, and of course there's going to be losses, H sub L. When you say H sub L, that refers to the major loss and the minor loss. So if we isolate this H pump, then what we get is something like this: P sub 2 minus P sub 1 plus V sub 2 squared minus V sub 1 squared all over 2G plus Z sub 2 minus Z sub 1 plus head losses. Right, so that's it. So this one is what we call the pressure head, and this one is what we call the velocity head, and this one is the elevation head, and this is what we call the head loss. Right, so if that's the case, then for the pressure head, it's just H sub P. We use H sub P, right, in this equation, H sub P, and this one is H sub V, and this is H sub Z, and this one is H sub L. Right, so when we say static head for pump systems, we are referring to the pressure head and the elevation head. So H sub P plus H sub Z, that's our static head, plus the dynamic head, consisting of this velocity head and this head loss, HV plus HL. Right, so here's our static head, or total static head, and total dynamic head. Right, so that's going to be our working equation or general equation. But for systems like, for example, let's say this lower reservoir or this lower tank is exposed to atmospheric pressure, and this one is also exposed to atmospheric pressure, then that means this is 0. Right, so that's why in some equation they just say that the static head is just simply the elevation head, just simply because the pressure at this point is atmospheric pressure, and this is also atmospheric pressure, so that means P sub 2 minus P sub 1 is just 0. So that's why sometimes you're just left with this elevation head. Alright, so just take note of this most general equation. So going back to this lecture materials, lecture handouts that we have here the various head terms in a pump system. So here's our reservoir at the suction side, and here's our reservoir at the discharge side. So when you say elevation head, this just simply the difference in the elevation, let's say right here we have the highest point, and also right here, here's going to be our consideration for the elevation. So it must be this water surface, because from this water surface to that, there's going to be sorry what I was saying is that this elevation of water, so from this elevation of water, we are trying to discharge this into this height right here, right? So it's not this height, but rather this height right here. So it's not always the case, because that depends upon the configuration of the pump systems, right? So but for this case, we are trying to lift this water from this elevation, or from this position, into this highest position right here, right? So that's the elevation difference. And for the pressure difference, then, as I've said, if there's a pressurized systems right here and pressurized systems in this discharge side, then of course there's going to be the equation P sub 2 minus P sub 1 divided by this unit weight is not going to be 0, right? So there's going to be a value for that if there's a pressure difference for this. But if it is atmospheric, let's say this is atmospheric, this is atmospheric, then that means this is just 0. Okay, so this is gauge pressure. Okay, so what else we have here? The velocity head and the head loss, and recall that this equation is just v2 squared minus v1 squared all over 2g plus this head loss terms. So you just sum all that up, and that's gonna be it. Right, so what else? Okay, so you might heard the term suction head and suction lift. So what's the difference? The suction head is basically, if here's our pump, then if the suction side is higher than this pump level or this pump center line, then that's what we call head. So it's a head term. So something like it's more on the weight, right, or pressing this downwards. So that's more in head term, static suction head. But when I say suction lift, that means that the suction or this reservoir is actually lower than the pump center line. So meaning from this lower bottom, it's going to be brought up. So that's going to be lifting, right? So that's this static suction lift, right? And moving on, we have this brake horsepower, which is just simply the horsepower at the shaft of the impeller. So right here, let's say we have this electric motor, here's our pump, and here's our impeller right here. So the water power is the power transferred, or the energy transferred to that moving fluid, whereas the brake horsepower is the power available at the shaft of this impeller. And of course, there's still another power, like for example the power input to the motor, and that means that of course there's going to be efficiency or losses. So let's say we have here in the power input, let's say 1 kilowatt, and that means that right here at the brake horsepower is just less than 1 kilowatt, let's say 0.8 kilowatts, and here probably 0.7 kilowatts or whatever. Anyway, that's it. And we also have other terms right here. I mean another parameters, like for example net positive suction head and specific speed. So you just have to read all that, right? So I think that's all for now, and we'll move on to our sample problem.